You ever get that weird feeling that the world around you isn't, quite real? Like maybe, just maybe, everything we see and touch is all part of some giant, unbelievably complex computer program. It's a question that's moved way beyond late-night chats and into some of the most advanced physics labs on Earth.
Yeah, we all know this line, right, from The Matrix. It's been a classic sci-fi question for decades, and it taps into this really deep-seated philosophical worry about what our reality actually is. But what if I told you that this whole idea is literally leaping off the screen and into the real world of physics?
Well, that's exactly what's happening. The simulation hypothesis is officially leaving the movie theater and walking right into the laboratory. It's becoming a serious, and maybe even a testable, scientific idea. That's right, more and more physicists are looking at the fundamental laws of our universe and finding these clues that it all operates suspiciously like a computer. Now, this isn't about proving we're characters in some cosmic video game, but about trying to find an even deeper level of reality. And get this, one of the most exciting new clues comes from a place you'd never expect: gravity. A new bit of research gives us this amazing way to think about it, and it all starts with something as simple as your morning cup of coffee.
So, a physicist named Dr. Melvin Vopson has put forward something pretty radical. He's suggesting that gravity isn't a fundamental force at all. Nope. Instead, he thinks it's just a byproduct of the universe constantly trying to run more efficiently. Basically, he's arguing that gravity is the universe's way of compressing data to save on processing power. Vopson's whole theory is built on this new principle he calls the second law of infodynamics. It's a proposed new law of physics that's all about information, and it basically turns one of the most famous laws we have completely upside down.
And this really shows you the difference. We all know the second law of thermodynamics, right? Physical systems always move toward more disorder, more entropy. A clean room gets messy, an ice cube melts, but Vopson's law of infodynamics says the exact opposite is true for information. Systems naturally move toward less informational disorder. They actually get tidier. So let's go back to that coffee cup, okay? When it's piping hot, the molecules are all buzzing around with wildly different energy levels. To describe that whole chaotic system, you need a ton of information. That's what we call maximum information entropy. But as the coffee cools down, the energy evens out until all the molecules have pretty much the same energy. The system becomes simple, uniform. You need way less information to describe it, and that's minimum information entropy.
So Vopson says gravity is just the same principle, but playing out on a massive cosmic scale. Think about it. When particles are just scattered randomly across space, that's a really complex, high-information state. But when gravity pulls them all together to form planets and stars and galaxies, the system gets way more ordered, and the information needed to describe it gets way more compact. You could almost say gravity is the universe running a cleanup on its hard drive. Okay, so this leads us to an even bigger, even wilder idea. If the universe is constantly processing information, does that mean it's digital? Could reality itself actually have a resolution limit like a TV screen?
This is the whole concept of quantization. And it suggests that if you could zoom in far enough on reality, you wouldn't see a smooth, continuous picture. You'd find that space and time themselves are made of these tiny, individual chunks, these fundamental pixels of existence. And the size of one of these space pixels actually has a name. It's called the Planck length. It's the absolute smallest possible distance in theory. If you go any smaller than that, our entire understanding of space and location just breaks down. We're talking about a decimal point followed by 34 zeros and then a 1/6. I mean, it's a number so ridiculously small that it's almost impossible to get your head around. So let's try an analogy to make sense of it. Just let that sink in for a second. If you could blow up a single Planck length to be the size of a grain of sand, a single atom on that same scale would be bigger than our entire Milky Way galaxy. That's the fundamental resolution of our reality. It's just staggering. And it's not just space either. Time is also pixelated. The smallest unit is called Planck time.
What this means is that time doesn't really flow smoothly like a river. It clicks forward in these tiny, discrete steps. It's kind of like the universe's frame rate, ticking along at a speed we can't even begin to comprehend.
Now, this isn't just some wild idea. The theory of loop quantum gravity is built on this exact concept. And by making space-time chunky, it actually solves one of the biggest headaches in all of physics, the singularity at the center of a black hole. Think about it. If there's a smallest possible piece of space, you just can't cram an infinite amount of stuff into it. The infinity problem just goes away.
So, if space-time is pixelated, and gravity is all about processing information, what does that really say about the nature of reality itself? Well, it leads us to one of the most profound ideas in all of science. This is the famous it from bit idea from the legendary physicist John Archibald Wheeler. What he was proposing is that at the most rock-bottom level, the universe isn't made of matter or energy. It's made of information. Every single physical thing, every it, springs into existence from simple binary choices, from bits.
But the source code of reality probably doesn't look like the ones and zeros on our computers. Some of these theories suggest it's more like a language based on pure geometry, that the fundamental building blocks of everything are these incredibly complex and beautiful structures, almost like a symbolic language that writes all of existence into being.
And there's even more evidence that points in this direction. First, you've got the holographic principle, which suggests our entire 3D reality could just be a projection from a flat 2D surface. Then there's Landauer's principle, which proves a direct physical link between information and energy. Get this, just deleting one bit of data actually creates a tiny puff of real heat. And, my favorite, the lazy evaluation theory. The idea that reality only renders itself in high def when we're actually looking, just like a video game engine trying to save on power. What all of this is screaming at us is a really profound conclusion. Information isn't just something we use to describe the universe. These principles suggest that information is a physical, fundamental part of the universe itself. It's as real as an electron.
Okay, so when you start putting all these different pieces together, you get this radical new way of looking at everything. So what's the end game here? Why are scientists even chasing this strange and beautiful idea?
You know, the real prize here isn't just to be able to say, "Aha! I knew we were in the Matrix." The real goal is to discover the underlying operating system of reality itself. Thinking about the universe as a giant computation could finally be the key that unlocks the biggest puzzle in science: how to unite Einstein's theory of gravity with the weird world of quantum mechanics.
And that leaves us with one final, truly awe-inspiring thought. If our reality is just the output of some cosmic computation, if its laws are just an algorithm, and its very fabric is information, what happens when we, the inhabitants of this thing, finally figure out how to read, and maybe even write, the code itself?